Okay, I hear the recording in progress. Okay, so we're up to 8.2. I may actually come close to finishing 8.2 today. If not, I probably should be able to finish it tomorrow. Okay, so we're maybe a little bit ahead. Let's see how it goes. Okay. And homework is here. I'm also going to include problem 14. Sorry, that's one more problem to add in, but guess what? I'm going to end up doing it anyway. So that's that. Okay, so we're doing surface area of revolution. I did one problem, and I'll do many more today. All right. So here we go. So key things that you need for this section. Surface area of revolution. So again, we're revolving about either the x-axis or the y-axis, just like before, but now we're doing surface area. Okay, so page 553, use this if you're rotating about the x-axis. You can use this one also. It depends on whether you have y as a function of x or x as a function of y. This is x as a function of y. Okay. And for rotation about the y-axis, you use this one. Okay, and this thing sometimes is called ds. Okay, so ds is either this or this. Okay, and you recall from section 1, for the integration, you didn't have the 2 pi y stuff or the 2 pi x stuff. You just integrated this. So for surface area, you just add this extra factor, either 2 pi x or 2 pi y, as the case may be. Okay. Right, so here we go. All right, so let me see where I picked up from last time. Okay, problem number 12. Okay, so y equals x cubed over 6 plus 1 over 2x. Spin about the x-axis from 1/2 to 1. Okay. So I'll just give you the setup. All right, rewrite this as 1/6 x cubed plus 1/2 x to the negative 1. dy dx. 3 times 1/6 is 1/2 x to the 1/2 minus 1/2 x to the negative 2. If you square it, dy dx squared, this thing squared is 1/4 x to the 4th. This thing squared is 1/4 x to the negative 4. And then this recurring theme that Mr. Stewart likes a lot, the 2ab term turns out to be just negative 1/2. 2 times 1/2 is 1, times 1/2 is negative 1/2, and x to the negative 2 times x to the 2 is x to the 0, which is 1. Which again means if you add 1, that minus just changes to a plus. So 1 plus dy dx squared is 1/4 x to the 4th plus 1/2 plus 1/4 x to the negative 4. And this refactors. And if you look at this and you say, I don't know how I can factor that, it's pretty simple. All you do is look back at what you have here and then change the minus to a plus. In other words, it's going to be 1/2 x squared plus 1/2 x to the negative 2 squared, which is exactly the same thing as this, except change it to a plus. And again, if you're not convinced of that, just multiply it all out. Okay, double check that. What is this thing squared? That. What is this thing squared? That. And what is the 2ab term in the middle? 2 times that times that. 2 times 1/2 is 1, times 1/2 is 1/2, so there's 1/2. And then x to the 2 times x to the negative 2 is x to the 0, which is 1. So it does work out. Okay, so we're spinning about the x-axis, which means we integrate 2 pi y. So 2 pi, here's the original y. And then, this is not a mistake, by formula, it's a square root of this thing. It's a square root of blah, blah, blah squared. And so in red, that cross off means I got a square root squared. So if you have a square root squared, you just lose it. And I don't have to worry about absolute value because I just have positive expressions. Okay, so I took out the 2 pi, x cubed over 6 plus 1 over 2x times 1/2 x squared plus 1/2 x to the negative 2. Okay. And then I just et cetera after some point. I did FOIL it out. So first comes out to be 1/12 x to the 5th. Outer comes out to be 1/12 x cubed times x to the negative 2 is x to the 1. Inner, that times that is 1/4 x. 1x cancels that x, so you still have an x. And then last, that times that is 1/4 x to the negative 3. And I just say et cetera. Okay. All right, so that's that. Yes, I included 14 as a problem that you're responsible for. It's even. That's a mean trick. I'm doing it right now. Okay, so there it is. The reason why I want to show you that one is it's x as a function of y. Okay, we're still spinning it about the x-axis though. So look at 14. X is a function of y. Y goes from something to something, but you just pretty much do the same thing. It's a role reversal. So the form of the ds, little change in arc length, that I'll be using would be this flavor, right? Instead of radical 1 plus dy dx squared dx, I do 1 plus dx dy squared dy. And the dx dy even sounds funny. The only reason why it sounds funny is because we're used to saying dy dx, right? Up to now, you've just been saying dy dx, dy dx, dy dx. And now when we say dx dy, that sounds weird. Of course, if we could have developed a calculus where it was always x to the function of y, and then dx dy would sound usual, right? We keep saying dx dy, dx dy, dx dy, and then all of a sudden, if you say dy dx, that sounds weird. But there's nothing weird about either of these. It's just the frequency at which you hear it, I suppose, right? You've heard this all your calculus life, so to speak. You just hear dy dx, and then when you hear dx dy, you say that sounds strange, but it doesn't have to be strange. It's just because we almost never do x as a function of y. But logically, if you go from a logical standpoint, not from frequency, how frequently you hear it, just dx dy is perfectly good if you have x as a function of y, just like dy dx is perfectly good if you have y as a function of x. It's just that we're used to hearing dy dx more often. So you think that's, quote unquote, regular or normal, so to speak. Okay, so anyway, so here's 14. 12 is crossed out because that's what it was in the previous edition. So x equals 1 plus 2y squared, y going from 1 to 2, spin about the x-axis. So if we spin about the x-axis, it's 2 pi y. This time, I don't have to replace the y because I'm integrating dy. I'm still spinning it about the x-axis. Okay. Over here, when I did 2 pi y, maybe I should write this here. It is 2 pi y. Here's y, but I have to change it to x because I'm integrating with respect to x. Here, this 2 pi y, I just leave it alone because I'm integrating with respect to y. All right, so surface area is the integral from a to b of 2 pi y, radical 1 plus dx dy squared dy. Once again, you're welcome to put this on your next cheat sheet if you wish, but I don't think you have to. If you just know, oh yeah, dy dx squared dx, then you just think to yourself, oh, I have x as a function of y, just make it dx dy squared dy. But whatever you wish to do is fine with me. Okay. All right, so 2 pi y. So what is dx dy? 4y. And 1 plus dx dy squared is 1 plus 16y squared, right? So that's pretty straightforward, I think. All right, so surface area is 2 pi y. Notice I don't change it like I did over here. So how come I change it over here? Because I was integrating with respect to x. It's 2 pi y. Here it's still 2 pi y, but then I realized, oh, I'm integrating with respect to y, so just leave y as it is. Don't change it, so that it has something involving x. So 2 pi y radical 1 plus 16y squared dy. Okay, and normally you take out the 2 pi, and I notice a simple substitution ought to do it. The derivative of 1 plus 16y squared is almost y, except I have to put a constant, which happens to be 32, but that's no big deal. All right, so u equals 1 plus 16y squared, u substitution, du is 32y dy. So there's the y, there's a dy. So I need a 32 inside which means 1 over 32 outside. And I need to change the limits. So let's see, the original y is going from 1 to 2. So what happens to u? Well, I plug in. So I plug in 1 plus 16 is 17. Plug in 2. Let's see, 2 squared is 4 times 16 is 64 plus 1 is 65. Okay. Notice by doing a substitution, you could have a completely different kind of interval. The original was only going from 1 to 2. You know, the length is only 1. Now all of a sudden you're going from 17 to 65. That's perfectly okay. That has to be because of this relationship between u and y. Okay. So as y travels from 1 to 2, u travels from 17 to 65, a big difference. So outside I now have what? 2 pi over 32, which is pi over 16. Radical this, which is radical u, 32y dy, 32y dy, that's my du. And there we go. And that's u to the 1/2. So u to the 3/2 divided by 3/2 means times 2/3. A little bit of touch up here. 2 cancels to 16, giving me 8. So I have pi over 24. Look at 65. 65 to the 3/2 minus 17 to the 3/2. And you should know now the rule of writing this. I do want you to have something raised to the 3/2, like 65. 65 radical 65 minus 17 radical 17. So this is the final answer. Pi over 24, 65 radical 65 minus 17 radical 17. Okay, so you need to do this final step. Now, if you don't do it, I'll give you most of the credit for getting this far, but you should do this. Again, it's the whole idea of simplifying. Okay, simplifying for the average person on the street, so to speak. A random person may not be taking calculus, and you ask them, which of these do you understand? They're more likely to understand this than this. Okay, 65 radical 65. Okay, I think I got it. 65 to the 3/2, right? A lot of people don't know that. Even people who've taken math may not remember that. And likewise, 17 radical 17. Okay. All right, so yes, I did a mean trick. I threw in 14, but guess what? I just did it. So that takes care of that. Okay. All right, so I was going to do a few more from here, and I don't have to do that much more. Let's see, I did for you yesterday. That one, okay, so 13. Oops. 15. Where'd it go? 13. Again, x is a function of y. X equals 1/3, blah, blah, blah. Y goes from 1 to 2. So once again, we're not comfortable with that. So we're going to integrate with respect to y. I mean, the only difference between 13 and say 11 is 11 we're more used to y as a function of x. 13 you have x as a function of y. We still pretty much do the same stuff. Let's see. Actually, I take it back. Sorry. I'm showing you 13 star. Okay, so this is not a problem in our text because Mr. Stewart took it out from a previous edition. And I'm just looking carefully now. Yeah, so 13 star. It's a good problem. So y equals cube root of x, y between 1 and 2, and this time you're spinning it about the y-axis, about the y-axis. So that means I'm integrating 2 pi x. So remember, if you revolve about the y-axis, integrate 2 pi x, and then ds which can have either this form or this form. That was on page 553. All right, so since I'm integrating with respect to y, I need to solve for y. That's easy. Cube both sides. X equals y cubed. So x equals y cubed as y goes from 1 to 2. Cube root function looks something like this. All right, so dx dy, 3y squared. Add 1 to the square of that. So 1 plus this thing squared is easy. 1 plus 9y to the 4th. Okay, so the integral is 2 pi x, and what's x? Y cubed. Square root of this, that looks like the formula for arc length, section 1. Radical 1 plus 9y to the 4th, dy. Okay, this kind of looks like a recurring theme, something we've seen before. Okay, so let's see. The derivative of this stuff, a 4th degree, is going to be 3rd degree. So again, u substitution. Now take the 2 pi out. U equals 1 plus 9y to the 4th. Du equals 36y cubed dy. There's the y cubed. There's a dy. There isn't a 36, so put a 36 inside, 1 over 36 outside. Remember, you can only play this game of putting something inside and outside with constants. Variables you're not allowed to. So for instance, you can't sneak in here x squared and put outside 1 over x squared. It doesn't work. It doesn't give you the proper antiderivative, okay, because of chain rule. But only constants. So you can put pi and 1 over pi, or radical 2, 1 over radical 2. But you can't put, let's say, 10x, 1 over 10x. Okay, that's not allowed. Okay, change the limits. Y equals 1. U is 1 plus 9, 10. Y equals 2. Well, let's see. 2 to the 4th is 16. Times 9 is 144. Plus 1 is 145. So again, please notice the original integral, pretty small, only 1 to 2. Now, all of a sudden, we're going from 10 to 145, right? So by making this transformation, you get quite a different range for your limits. Okay, so what happened? 2 pi comes outside. So 2 pi comes out, multiplied by 1 over 36. That gives me pi over 18. And now I'm integrating from 10 to 145. Radical, this mess is now radical u. And now I have the 36y cubed dy. You see, I can't change 36y cubed dy to du unless I see literally the whole thing, right? The original had y cubed dy, saying, stop. You cannot change the du unless there's a 36. You must have the 36, right? So put in the 36, 1 over 36. Now that I see 36y cubed dy, 36y cubed dy, I can change it to du. All right, as we said before, no big surprise. It's going to be a 3/2 exponent, right? That's u to the 1/2. So same stuff, u to the 3/2 times 2/3. 2 and so cancels to 18, 9 times 3 is 27, 5 over 27. 145 to the 3/2 minus 10 to the 3/2. We know what that's all about. 5 over 27. 145 radical 145 minus 10 radical 10. And that is that. Okay. And here we go. Okay, so I want to show you one more where we spin about the y-axis. Oops. 17. Okay, so we spin about the y-axis means you're integrating 2 pi x. So 17x equals radical a squared minus y squared. Y goes from 0 to a over 2. Okay. Let's see what happens here. So x equals a squared minus y squared to the 1/2. spin about the y-axis. So dx dy, I know it sounds funny, 1/2 a squared minus y squared to negative 1/2 times the derivative of the inside with respect to y. A is a constant, so negative 2y. Cancel out negative y over radical a squared minus y squared. I'm supposed to square that expression. That's nice. I get to lose the minus sign. I get to lose the radical. So dx dy squared is y squared over a squared minus y squared. By formula, I add 1. Okay, here's 1, right? How come I write it like that? To get a common denominator. 1 plus dx dy squared, right? So add 1, a squared minus y squared over itself, plus that. Notice the y squared cancel out, so I have that. Okay, so by formula, the surface area is the integral from 0 to a over 2 pi x. X because I'm spinning about the y-axis. 2 pi x radical a squared minus y squared times the square root of all this stuff, dy. Very conveniently, that cancels with that, right? See that, cancels that. Square root of a squared is a. So I'm integrating 2 pi a, which is a constant with respect to y. So 2 pi a y from 0 to a over 2. Plug in 0 for y, you get 0. Plug in a over 2, you have 2 pi times a over 2 pi a squared. Final answer. Okay, so the problem's actually finished, but I'm going to dig a little bit deeper. Okay, I'm going to show you something else, which is a modification of what I originally had. Okay, folks, I'm actually pretty close to being done. So I'm finished with the problem, but I'm just digging deeper. Suppose instead of the limits that they gave us, suppose it said go from negative a to a. Of course, the integration is all the same. Okay. A little bit of algebra will convince you that this is x squared plus y squared equals a squared. Square both sides, right? X squared equals that, and then add y squared, you get this. Well, that's a circle. Center of the origin, radius of a. So I have this semicircle. If you spin it about the y-axis, you get a sphere, which means we can compute the formula for the surface area of a sphere. Well, all the analysis is exactly the same. Just copy and paste everything over here if you would. Okay. The only difference is the interval. I can go from negative a to a, or because of symmetry, I think I'm just going to go from 0 to a multiplied by 2. Okay, so the step that I left off over here, I had integral of 2 pi a dy back over here. All of this calculus is the same, except for the limits. 2 times integral from 0 to a of 2 pi a dy. So just like before, the integral is the same. 2 times 2 pi a y from 0 to a. Plug in 0, you get 0. Plug in a right there, you have 2 times 2 pi, 4 pi, a times a, 4 pi a squared. Okay. So which means, back in this picture, the radius is a, surface area is 4 pi a squared. In other words, we actually have proven, we've proven the formula for the surface area of a sphere is 4 pi r squared. Okay. And some of you might remember that formula from 6th grade or 7th grade or something like that. Okay, so by means of the calculus here in Calc 2, you finally get to see some of the derivation of the formulas that you first had, right? So maybe in 6th grade, 7th grade, you heard the formula for the volume of a sphere is 4/3 pi r cubed, and I give you a derivation of that formula. You could do either the disk method or the shell method, okay? And now your Calculus 2 teacher has now shown you a formula for the derivation of the surface area of a sphere, 4 pi r squared. So back in 6th grade or 7th grade, when you first got this formula, right? You'd say, oh, if you have a sphere, volume 4/3 pi r cubed, surface area 4 pi r squared, right? Here's a formula, use it. So at the time, you said, okay, I'll use it. I know how to plug in, no big deal. But you might have thought, how did they come up with that formula, right? Where's this formula? Why is it 4/3 pi r cubed? How come it's not 8/3, or how come it isn't 7/316,521 r cubed or whatever, right? Okay. And now in calculus, we can prove that the formula for the volume of a sphere is 4/3 pi r cubed. And we've now just proven the surface area of a sphere is 4 pi r squared. I think I said cube, I want the sphere. The volume of a sphere is 4/3 pi r cubed, right? Okay. So anyway, I'm not holding you responsible for all this, but I just wanted to show you, it is kind of neat that by calculus, those early formulas that you had, like, I also showed you what the volume of a cone, which was 1/3 pi r squared h. Okay. So you had all these formulas from 6th grade, 7th grade, something like that. Volume of a cone, volume of a sphere, surface area of a sphere. And say, how do you come up with those formulas? They come about by calculus. So we've proven in this class the formula for the volume of a cone, volume of a sphere, surface area of a sphere, and so on. Okay. I have not shown you yet the circumference of a sphere, 2 pi r. Guess what? That's going to be involved in your next quiz. Okay, so you will help hopefully derive the formula for the circumference of a circle, which is 2 pi r using arc length. So that will be part of the quiz this coming Friday. In fact, that's basically the quiz for this week, to come up with a formula. So you heard before, that's another formula you had back in 6th grade, right? 7th grade, something like that. If you have a circle, circumference is 2 pi r. And so, where does that come from, right? How do you come up with that? And so we now have techniques to derive that formula. Okay. All right, so that is that. I might as well go back and show you the other one. It wasn't on my original list, but I might as well do it. Okay, so y is 1/3 x to the 3/2, x between 0 and 12. Spin about the y-axis. Okay, I don't have this one pre-done, so we'll just go ahead and do it now. So this is problem 15, page 556. So y equals 1/3 x to the 3/2. And x is between 0 and 12. And we're asked to spin about the y-axis. Okay, so whatever this thing looks like, spin it like this, so you get some weird shape. We're not talking about volume now, we're talking about surface area. All right, so dy dx, that's easy. So that times that is 1/2 x to the 1/2, which is 1/2 radical x. 1 plus dy dx squared is 1 plus, that's easy to square, 1/4 x. Okay, so the idea again is if you were to chop this into many, many pieces, right? This is delta x. My radius is x. All right, so surface area is the integral from where to where? 0 to 12 of 2 pi. Okay, spin about the what? Spin about the y-axis of 2 pi x radical 1 plus 1/4 x dx. All right, so how do I integrate something crazy like that? Let me try to take care of this first. So integral from 0 to 12, 2 pi x, and get a common denominator 4, right? 4 plus x. Is that right? Oh, double check, divide. 4 over 4 is 1, x over 4 is 1/4 x. And watch what I'm going to do. Right? 2 cancels square root of 4 on the bottom. And yeah, take out the pi. Four plus x, let me write it as x plus 4. Dx. Now you say, how do you integrate this? This is one of those where I want to make a substitution. I have the complicated thing. Oh, not too complicated, but it's x plus 4. It's more complicated than x. I want to make this nice, like u. This will not be nice, but that's okay. At least it's not part of the square root. Okay, so u equals x plus 4, du equals dx, and that means x is equal to u minus 4. Okay, when x is 0, u is 4. When x is 4, oh, sorry, x is 12. U is 16. That's nice because when I take a square root, there's only a 4 and a 16, which is what you like. Okay, so the new integral is pi. I'm now no longer going from 0 to 12. I'm now going, u goes from 4 to 16 of x, u minus 4. Radical x plus 4 is now radical u du. And now that's easier. So look at, by making that transformation, right? The complicated stuff was under the radical, and this is nice. I made the stuff under the radical nice. This was not as nice, but if I'm going to have a not nice part, I want it out of the radical. And now this is pretty easy to combine. Go like that and like that. Remember, this is like u to the half, right? So pi integral from 4 to 16. U, oops. Just to focus here. U times u to the half is u to the 3/2 minus 4 u to the half du. Okay, then we're pretty much home free. Pi u to the 5/2 divided by 5/2 minus 4 times u to the 3/2 divided by 3/2, 4 to 16. Go like this. Okay, plug in 16. 16 to the 5/2 minus 2/3 times 16 to the 3/2 minus, plug in 4. 2/5 times 4 to the 5/2. Sorry, this should be 8/3, right? Sorry. 4 times 2/3, 8/3. Same thing here, 8/3. 4 to 3/2. Bracket. Double check too. 16 to 5/2 minus 8/3, 16 to 3/2 minus 2/5 times 4 to the 5/2 minus 8/3, 4 to the 3/2. Yeah. (16 to 5/2 means square root of 16, which is 4. 4 to the 5th power, 4 times 4 times 4 times 4 times 4. Punch it in your machine, 1024. 16 to 3/2 means square root of 16 is 4. 4 cubed is 64. Two fifths. Square root of 4 is 2. 2 to the 5th is 32. 4 to the 3/2. Square root of 4 is 2. 2 cubed is 8. Okay, and I'll just say etc. The rest, you can, it's just arithmetic, get a common denominator. Common denominator would be 15, I guess. And multiply, that times that, and so on. And there we go. Okay. All right, folks, I think I've actually done all I needed to do in this section. And I'm pretty much done with it. So it looks like I'm a day ahead. I can actually get started with chapter 9 tomorrow. Yeah, so I'm a little bit ahead. So I think that's fine from there. All right, I'm done for the day, folks. Let me stop the share and see if anybody has any questions. Otherwise, we're finished. So let me check the chat. Don't see anything in the chat. Okay, anybody with a question, please? All right, so we're done, folks. So have a good day, and we'll see you next time. Okay, bye, everybody.
Professor. Thank you.
Thank you.